So it's pretty much important to understand why does a battery catches fire. We have been listening to this event happening nowadays very frequently, uh, with most of these two-wheelers, especially in India, are catching fires, and the fire numbers are increasing when you're talking about the month of May, June, where the heat is pretty much higher, and even the temperature rise uh, in such scenarios is pretty much high. So let's all understand, why does a battery catches fire. Now we have already witnessed lots of media coverages and lots of news that comes around for battery catching fire, for the two-wheelers in India especially are having an issue with the fire that is happening. So why does it happen? So the primary question that we are trying to ask here is why, sorry, why a battery catches fire. All right, so the answer is pretty much clear. Something has to do with the battery, and probably something has to do with the chemistry of the battery, because we have not seen, we have used battery in different applications before, be it hand tools, be it inverters at home, but we have never, or at least very few incidents have been reported for the fire in those scenarios. So what is the difference, and why it is happening that the vehicles, or especially the electric vehicles we're talking about, which has batteries, are a frequent are in frequent news for the fire cases. So the basic difference that we have is the current vehicles, electric vehicles, they are made up of lithium ion cells. And what about the earlier batteries that were made up of? They were made up of lead acids, right? So now lithium ions, we already understand that there's a difference in chemistry. Let's go in slightly more detail. Why lithium ion and why not lead acid? I mean, the primary reason is that lithium ion has much more energy capacity uh, per unit space or weight than the lead acid batteries. For the similar capacity, it will have a huge uh, space requirement, and the energy density overall, of course, the lithium ion is higher than in case of lead acid batteries, right? So that's a major reason that lithium ions are much more favorable in terms of the energy density when we call about electric vehicles, where the space is one of the major constraints in terms of the usable space that we have at the user. Okay, so before we jump into the chemistry, let's talk about what the overall battery is, and maybe just make sure that we make some terms pretty much common um, defined here. So we have a typical, I would say, a typical battery. Give me a straight line, yeah. So this looks like a typical battery that we have, right? Uh, I mean, I'm just making a rectangular shape, which is very, very common, but you can have any shape you want, but the idea will remain the same. You have one side which is a positive, you have another side which is the negative, and then you have a communication that happens, and mostly in the vehicles right now they are called as CAN, controlled area network communications, that happens with the battery. So what are inside the battery? Now if you see the cross section of a battery, there are a lot of cells in the battery itself, right? And these cells are the unit structures that are made up of the chemistry that we're talking about, lithium ion in case, and lead acid is another case. So the cells are the unit assembly blocks for the batteries, right? And there are a huge number of cells depending on the series and parallel combination. And the series parallel is defined by how much voltage you need at the end, and parallel is defined by how much current you need overall, right? So now we understand that each each battery is made up of number of cells. Now there's also a unit which controls and monitors this battery, and that is actually nothing but a BMS, which we call it as battery management systems, right? So this is a piece of hardware which has all the logic and capabilities to monitor and prevent battery from going into an unfavorable conditions. And we'll come back to that BMS later. Now, to catch a fire, in terms of technical terms, we call this as thermal runaways. So what is a thermal runaway? And it's not that only lithium-ion battery catches fire. As I mentioned, that it's have been very common recently, but it's not that. Thermal runaway is not a part of lithium-ion battery terminology. It's common in even lead-acid batteries as well. The thermal runaway defines that a battery or a cell reaches a certain condition which will cause an inevitable fire, and that fire eventually will trigger more fire or more favorable conditions for the fire to produce, and therefore this is a positive loop or a positive feedback is created, which is eventually leading up to a fire incident. So this is almost like a positive loop. Which will eventually lead to fire. Right, now let's go back and see why does a lithium ion has more tendency to create that favorable loop for the positive feedback, and which eventually will create a fire. Now to do that, we have to go deep inside the cell level understanding. Now we'll talk about cells for a minute. And before we talk about cells, for lithium ion, I think it's very much important to talk about what is cell in general made up of, and why is it even required in that scenario. So just to give you a basic brush up of cell or battery chemistry, you have a thing called as anode, a thing called as cathode, and then you have electrolyte in between them, which helps transfer ions in between them, right? So these are the only three major components in a cell. Of course, there are a lot of other things that comes into picture, but just for the sake of simplicity and understanding, let's make it very much simpler to understand. Now, what is the use of electrolyte? It gives you a medium to transfer the ions from one part to the other. Generally, in case of, let's say, charging, the cathode is a positive, so the ion, I would say positive charge, moves towards the cathode, which is negatively charged, right? And these ions move here, but then the ions, because it's positive charge, it has to release electrons, and these electrons are fed out through wires, and then maybe some external load that are kept external. This is a part of battery. Right. So electrons move in this direction and then comes back, but the ion, whichever is ion here, will move towards the anode in the electrolyte. Now, to facilitate that, there is actually a separator which is in between. Now, these are important terms. So, separator does allow the ions to pass through, but does not allow the electrons to pass through, and that's where you get current outside the battery and therefore not inside the battery, because the electrons are not transferred through the cell but outside the cell, and therefore this acts as a separator, as it mentioned. And if, let's say, if for some reason this breaks down, this will create a short between a positive and a negative, and then this eventually will dead the battery. It will go into thermal runaway eventually. All right, so that's the basic understanding of a typical cell. Now let's talk about why lithium ion. What happens with lithium ion? Right. So again, we talked about a basic structure: anode, cathode, electrolyte, separator. This will be similar with any battery, any cell chemistry. So lithium ion is similar in that case. But the material with these made up of are different, right? And therefore they are different cell chemistries. So I will talk about very basic cell chemistry in lithium ion, which is NMC. Mostly used, at least 80 to 85% of the vehicles running recently have been using NMC chemistry. There's one more chemistry which is very famous at this point of time, LFP, right, which is kind of a new trend right now. But we'll talk about NMC first, and just to simplify this. Now, anode, cathode, electrolyte. So in case of lithium ion NMC cells, the anodes are made up of your graphite, right? It's carbon graphite. Cathodes are made up of your chemistry, which is your lithium, neodymium, manganese, and cobalt. So that's the structure. I think we'll talk about the composition in a bit, and that is also important. But we'll park this discussion of composition maybe in the next topic, because it requires a huge understanding of these chemistry. So for this topic, we will just stick to the understanding that it's made up of these three elements: electrolyte, generally lithium salts. Right. If you just compare that with a lead acid, so you will understand that a lead acid battery has an anode, which is normally made up of lead, and the cathode is lead dioxide, I would say. And then electrolytes are H2SO4, which is sulfuric acid. Now this is where the things get interesting. Why do we have more favorable condition for lithium ion to get to a thermal runaway than lead acid battery is defined in the chemical structure? And let me just write the overall chemical reaction that happens, overall chemical cell reaction. So in terms of lithium ion, graphite, which is your anode. Then you have lithium. I'm talking M as any chemistry, NMC, LFP. So right now I'm just taking M. This is the part of M, right? Oxide, because the cathode is oxidized. And then you have reaction, which is lithium. Again, the X will talk about the combination C6. Lithium, again the combination, and then you have MO2. Okay, just to make it clear. Right, so this is where my whole understanding is, where in terms of charging and discharging, this is charge. This is discharge, right? So let me just move this guy slightly more aside. All right. Okay. Sorry for this time. All right. Now, in terms of lead acid, that's very much important to understand what happens in lead acid batteries. Now, in lead acid, you have a lead, and then you have H2SO4, which produces lead sulfate, and then hydrogen plus 2 electron atoms. Yeah. Yep. Sorry. Cut. Okay. Now, in terms of lead acid, now we have the overall reaction says that it's, as you mentioned, it is the cathode is made of lead oxide, and then you have H2SO4, which is your sorry, cut. Take out lead acid, yes. Okay, now in terms of lead acid, we have lead oxide, then we have H2SO4, which is our electrolyte, then we have lead, which is on the anodes, and this will correspond, so I'm just making it here because of the space constraints. I'm not just creating, right, so again, this is your discharge and this is your charge reaction. Now the interesting thing is, if you see in terms of the charge reactions, if you see from outside, you have got the overall all right. Now, after these a bit of boring chemical reactions, now let's come to the interesting part, because this is where things get pretty much more clear why we actually did this chemical reaction and what was the need for that. So in terms of this, let's talk about lithium ion side, and you can see that this is the overall reaction that we have. This is a part of anode because this is a graphite. This is part of, I would say, anode, so it just gets from anode. This is your part of cathode. This is your lithium salt, which is electrolyte. And this is where this guy is an excess fluid that comes out. Let me just write it clearly. Lithium, which is some kind of combination. M is your chemistry, and O2. Interesting. Now this is somewhere, this is the guy which is not a part of any three things that we mentioned, anode, cathode, or electrolyte. It's almost like degraded part of cathode, and therefore it does create a different lattice structure at cathode, right? That has a weak, I would say, O2 or oxygen molecules combination, right? And we'll talk now in detail about what happens with this. Now, before going to the lead acid side, just to give you some more, I would say, basic. The oxygen is the base for fire, right? Oxygen provides all the favorable conditions for the fire to exist, right? And this is where it gets important to understand that the lithium ion creates a structure at cathode which has tendency to release oxygen molecules almost at will if presented under very light severe conditions or stress conditions in terms of at the cell level. Now let me push it slightly here. I don't want it to be disturbing. All right. All right. Now this is where it gets interesting. Now in this case, let's bifurcate the lead acid side. Now this is a part of your cathode, as I mentioned, right? So this is part of cathode, C. This is your electrolyte, E. This is anode, makes sense. Now lead sulfate is very stable and non-flammable composition, right? And water is, of course, is very stable, and therefore it's almost one of the byproduct that we have in lead acids. So these two are stable structure in terms of lead acid. But when we talk about the lithium ion, we have one composition which is at cathode and which has a tendency to release oxygen very easily because of the combination of the cell chemistry that we have got. Now this is where we have at least reached to a point, right? All right. So now at least we have reached a point where we understood that there is some kind of difference in terms of lithium ion and lead acid, which in one case there is a favorable condition. Still, it is not bad. It is just providing enough, I would say, circumstances or environment for the fire to exist. It is not creating fire yet still. But in case of lead acid, it is very much difficult unless you actually create some kind of thermal scenarios where the water splits and produces an O2. The water decomposition happens and in lead acid, which is also a part of the lead acid thermal reaction. But that happens at least 1000 degrees C plus temperature, because water electrolysis is not very easy phenomena. Although in this case, the lattice, the structure that has made or degraded because of this water reaction, can release oxygen at a temperature of roughly around 115 degrees C plus, and which is where the things get interesting, because when we talk about the temperature in automotive, the automotive temperature can rise up to 100 degrees C at will because of a lot of other constraints, and the ambient that we are driving right now is very close to 50 degrees C even in normal conditions. And when you talk about the cell level or what is happening at cell, it must be reaching around 80-85 in a normal running scenario when we are talking about the severe places like Chennai and severe hot places when your ambient is higher. So of course the ambient temperature plays a huge role in this happening, right? Now we actually understand what is the cause, or what is at least the scenario where the O2 will release, and this O2 will favor the fire, or in terms of thermal runaway, it will start favoring that condition. Now then the ambient temperature is pretty much important. So let's come back and understand with this background what are the reason that we have a thermal breakdown in a cell, right? So let me delete this guy. All right, so what is the reason for thermal runaway? I think first thing is external, right? So why, of course, we are talking about an external factor. Other things are internal, right? In this case, external means ambient temperature, which is not in control of the battery pack itself. External mechanical stresses. Now eventually, in terms of internal, I think one which is very common is short circuit, and this can happen due to mechanical stress as well. Then we have overcharging, and I would say this is major cause of a thermal runaway. And then at last is the high C rate charging. Right, what is that? So when you are charging your cell or a battery at a higher rate than it is specified in the cell. So normal cell C rate is 1 or maybe 1.5 max to max, depending on the chemistry as well. But if you are going beyond that number and then you start charging the cell, it will get hot. Now let's go in detail how these factors affect that. Now we understand one factor where the oxygen production of oxygen or O2 molecules is a helping factor, right? How does each of these failures come to that scenario, right? So let me talk about an event here. So this can be any event on the top that we're talking about. In general, let's talk about now this event will cause a basic structure, I would say a small heat production. Or I would say spark in very small terms. Now this event can be anything, right? A small heat or spark is produced, which is not very bad. A small heat or spark can happen, can go down, and even can just disappear. Now this heat or spark is already produced. Now this will lead to something called as electrolysis breakdown if the temperature is not controlled. So what I mean by that is, let me go back again, and I'm drawing a battery. You have anode, you have cathode, right? One thing which I didn't tell you earlier is this separator, is that you have one layer that is made at anode and especially at cathode as well, which is SEI, solid electrolyte interface, and then you have a cathode electrolyte interface. Which does is it just provides an interface between the electrolyte that we have and the anode itself, and it does not allow a direct reaction between anode and electrolyte. It is almost like a interface wall between them. Now in case of lithium ion, if there is a chance that it degrades and there are some electrolytes which actually start engaging with anode, then you have a formation of gases which are ethane and methane, which are much more flammable and they are exothermic. Now that's important. Exothermic means they produce heat when they react. So electrolyte decomposition or interference or let me just move that. No, decomposition, I would say. Now these gases produced inside a small chamber of a cell, and they are very flammable, they are very exothermic, and therefore they start increasing temperature. Right? So this increased temperature, the moment the temperature reaches around 115, as I mentioned, and beyond, the oxygen starts cathode, degrades, O2 produces, and with the abundance of O2 in the small chamber that we have, and the combination of flammable gases, exothermic gases, and the O2, this environment is so much favorable that it produces more heat. And in turn, this more heat produces more decomposition of electrolyte and produces more of these exothermic and flammable gases, which in turn produces more increase in temperature, more oxygen produced, and this is a loop which is a positive driven loop, and therefore this loop is nothing but your thermal runaway. Right, and that's how once thermal runaway is kicked in, there's nothing else you can do. You just have to leave the vehicle and run away, because there is nothing else anyone can do, or any electronics can do, or any software can do once this has been triggered. And therefore it is very, very, very important for us to stop the thermal runaway somewhere here when it has not started the electrolysis breakdown. Due to any of these conditions that happens, as we mentioned on top, right? Few are in our controls and few are not. I would say mechanical stress, for taking care of mechanical stress, you have to take care of a good battery pack design. right? This we'll talk later in the course that we have. Till now, we do have how to make a better battery pack. Ambient temperature, you need to have good D rating. Right, this is a part of BMS, which we'll cover as well. Short circuit protection, again the part of BMS. BMS. And then overcharging, again part of BMS. Even the C rate, BMS. Now you understand that why BMS is very important. This gives us much more insight how and what BMS can do to prevent thermal runaway, and what thermal runaway looks like at a very minute cell level, right? Hope this helps, and eventually, the idea is to produce content which will help you and guide you basic understanding of things that are happening around us, and will give you a simple explanation of a complex problem statement that we have, so that we can create more innovative solutions based out of individual judgment. And yeah, thanks a lot for listening in. Thanks a lot for supporting us, and we'll keep this series going on. Thank you.